Okay, so welcome to the session. The session name is Creating Our Robot Overlords, and basically what I'm going to talk about is how to program a quadcopter, a parrot drone, using Java and give it some level of autonomy. And so also we're going to talk about some Internet of Things concepts and some autonomous concepts, autonomous flight concept, things like that. My name is James Weaver, and also I will be virtually presenting with Mark Heckler and Sean Phillips. They both co-created this presentation with me, but unfortunately were unable to come to Atlanta. So I've got videos of them in which they will address you and talk about different things, teach you different things about what they worked on in this project. And so my name is James Weaver. I'm a Java evangelist with Oracle. And the Twitter hashtag is DevNexusDrone for this. If you want to email me, use james.weaver@oracle.com, not jim.weaver, because jim.weaver, that's somebody else's email address. And as I said in my last session, that person, for some reason, does not forward emails for me, to me. So it just goes into dev/null. So please use james.weaver@oracle.com. So what's up on the agenda is we're going to talk about achieving autonomous flight. And we'll show you in context of this Parrot AR drone. And then we'll talk about how we use a Raspberry Pi and made it the brains of the drone. So strapped it on top of that. Now when I'm flying it for you today, the Pi and the power source adds a little extra weight, makes it a little less unstable or more unstable, and would tend to fly out in the audience and hurt people. So I'm actually, the brains of the drone is actually off board right now on my Macintosh computer. But the way that we developed it and the way I'll be talking to you about it is that it's all self-contained with the Pi and a power supply on the drone itself. So then I'm going to talk about what a quadcopter is, some of the physics of flight, and we'll talk about some Internet of Things concepts and tools and how we leveraged those. And then I'll show you a 3D flight simulation that Sean Phillips wrote to help us with the development, so we didn't have to continually fly the drone. We could use a simulation, 3D simulation, and then we'll talk about some next steps that we're going to be doing in this project. So first things first, we needed to choose a drone, and we also needed to find a foundational library, an API, that we could use to communicate from Java and to make calls that would communicate with that drone. And then we had to decide, how autonomous do we want this thing to be? And there are various levels of autonomy that I'll talk about. So the equipment list that we came up with was a drone, a brain, and some power. And I'll talk about our choices for each one of those. And then of course, we had to make it work, and that's where the story gets kind of interesting. So, which drone? We wanted one that was open source with a published API. We wanted a drone that had a community around it and that was fairly low price, because as I do presentations, I want people to be able to purchase what I've purchased and then play with it. And I wanted them to be able to do that without breaking the bank. So what we decided on was the Parrot AR 2.0 drone. It's about $240. It's a nice toy, but also you can strap a Pi on it and play with it and make it autonomous. And then which library? We wanted to make sure that it was going to be capable and also reliable, so that when we send commands to it and we use the API, we want it to be able to fly reliably. And also we wanted to make sure that the library that we chose was going to be supported, or at least they're going to be around in case we have questions. And so we decided on the Parrots on Java /Parroteer drone. If you go to Parrots on Java /Parroteer, that's where their API is. So that's the one we chose. And here's a message from Mark Heckler.
Hi, I'm Mark Heckler. I'm a software engineer at Oracle Corporation. and I've been working with Jim Weaver and Sean Phillips to bring some intelligence to drones. Oh, wait a minute. Wow, they're seated awfully close to the front. Have you all signed waivers?
Did you get your waiver? Okay.
Okay, well, that's great then. Let's carry on. Anyway, we wanted to provide some intelligence or add some intelligence to drones. What we settled on as a platform is the Parrot AR Drone 2.0. And that is a really nice, well-rounded drone, very capable, that you typically control with a cell phone or a tablet. And the way that typically works is you control all of the logic, the control on your device. And you connect to the AR drone via an onboard wireless access point that the drone has. So just like your router at home, you're connecting to it as a client. Once we chose the platform, we needed to choose the brain behind the operation, and that's where the Raspberry Pi comes in. The Raspberry Pi is a very inexpensive, very capable computer that, and very small and light, with low power consumption requirements, that allows you to load Linux on it and make several modifications and do several things that would be very difficult to do on another platform. So we loaded Raspbian, hard float, and JDK8 for ARM, and then we set about to make the hardware work. And the first thing you'll probably notice is that we have two Wi-Fi plugs here. What that allows us to do is tie one to an interface which acts as a client to the drone, just like your cell phone or your tablet would, and then to run host APD and an access point on the Pi so that we can connect to it from our laptop and control, take control if need be, but also to push software to the drone or to the brain and to debug it and profile it live and on board, which is extremely nice and very, very efficient. Now that gets the brain on the drone, but there's no way to power the brain from the drone. So what we had to do at that point was figure out a way to provide power to the brain. And that is where this comes in. This is your standard USB charger for cell phones, for mobile phones. And this one in particular provides 2600 milliamp hours, so it's got a good time range. And it puts out 1 amp of current, which if you're using Wi-Fi plugs that don't draw a lot of current, as these Devnexus don't, then you can run your Pi and the two plugs and everything you need off of this. So what we do to make the magic happen is we use Velcro, and we stick these two together, and then all I've done here is take a short USB cable and plug it in to the Pi and to the power source, and then we turn it on. And as you can see, that boots the brain. So at that point, to make the whole thing come together, all we really have to do is connect the brain to the drone. And now we have the makings of an intelligent drone. So at this point, the drone has a lot more capabilities than your standard. Oh my goodness. Well, I hate it when they become self-aware. Anyway, back to you, Jim. I hope you all have a great session. And again, to those of you in the front, good luck. Good luck.
So I'll carry back any gratitude that you have to Mark. Okay, thank you. So the equipment list that we used, as Mark said, was the Parrot AR2 drone, right there, and the brain is a Raspberry Pi Model B with a case, and also we had two Wi-Fi adapters that we put into the Raspberry Pi. Raspberry Pi has two USB adapters or slots, and so these Wi-Fi adapters will do Wi-Fi through the USB. And then a class 10 SD card. And then for the power, we use these lipstick charger, and as you saw in the video, and then just a short cable. and we needed to use some tape or Velcro to tape things together. And so, yeah, so the Raspberry Pi and the onboard programming was the central piece of the puzzle. And then there's the lipstick charger. And there's a bill of materials. And at the end, there's a link where you can see all the components if you want to build this yourself. The Raspberry Pi itself, we used the Raspbian, the typical configuration of Raspbian. And then we configured a couple of wireless access points. And again, that full documentation is available at bitbucket.org. And you'll be able to find that from the link. Basically, if you go to autonomous4j.org, I believe it is, then that's going to take you to that Bitbucket repository where you can see everything. We created a convenience domain. So making it work, we didn't anticipate many issues. And in hindsight, that was definitely just silly. We had API challenges, equipment challenges, firmware challenges. There were lots of challenges to make this thing work. The good news is that we've kind of worked out a lot of those challenges so that you could take the bill of materials and the software and just run it yourself. So we had some unrealistic expectations. We thought it'd be like Rosie the Robot or, you know, R2-D2, 3CPO. And what it ended up being was pretty much bad robot that cuts you. Those blades, I mean, Julie, have I been cut by those blades? Yes, yes. Yeah, with a bit of that thrown in. So the reason why I'm not flying with the extra weight here in this room, I don't want to hurt anybody. So this will demonstrate flight with the Raspberry Pi, so you can at least see that. See how kind of unstable it is? Notice also we're using monofilament wire so it doesn't wreck Mark's wife's drapes. So the anatomy of the quadcopter, as we mentioned, there are four spinning blades of doom. These are brushless motors, and there are motor controllers. Each motor has a motor controller right next to it there. There's a lithium polymer battery. It's a 1,000 milliamp. There's an onboard wireless access point on the drone so that you can do Wi-Fi to it. And it's got an indoor shell. This is the indoor shell. It's styrofoam. There's also an outdoor shell for flying outdoors where you don't need to protect it from bumping. Also, on the quadcopter, there's an IMU. It's an inertial measurement unit. And so that's got a gyroscope with 3 degrees of freedom. So that will measure roll, pitch, and yaw. Also, it's got an accelerometer with 3 degrees of freedom, so it can tell in the X, Y, and Z axis how much acceleration there is. And also, there's a magnetometer, which can then tell, because of north, it can tell, based upon north, which direction it's facing. Also, there's an ultrasound height sensor, and that's good for about 3 feet. And it does ultrasound, and then based upon when it gets the sound waves back, it can tell how high it is. And so hopefully you'll see some level flight here, and that's because of the ultrasound. We're going to take it off from here, but it'll probably maybe end up a little lower and then travel over there because of the ultrasound. On carpet, because carpet absorbs sound waves, sometimes it's not as accurate as it is hard floor. Also, there's a pressure sensor. The pressure sensor is for higher flight because it can, as it goes higher, then it can measure the barometric pressure and kind of estimate how high it's flying. And then there's a front camera, 720p front camera, And then there's a downward-facing camera, a 360p downward-facing camera. And the downward-facing camera is for odometry, so that it can estimate how fast it's going, or at least use that as part of the equation for estimating how fast it's going by the images going by. Obviously, other ways to tell how fast it's going are other parts of the IMU, specifically the accelerometers. So the flying principles are pretty simple. I mean, there are only 4 ways to control it, because there are 4 rotors. So if you want to, in aeronautical terms, if I want to roll, then I'm going to have to apply more velocity or more torque on these than I do these. So I increase these and it'll roll. Increase these and it'll roll with this way. Increase the back and it'll pitch forward or pitch up. And then for yaw, which is this movement, just change the opposite speed of opposite blades, and that changes the amount of torque, because these are spinning in opposite directions. So this is spinning the same direction as this, maybe counterclockwise, let's say. These would be spinning clockwise. So if you spin these faster, there's more torque in the clockwise direction, which then causes, if you add up all the torque, then it would cause it to move. And so that's the flying principle behind the quadcopter. So here's the demo. We'll see if anybody gets hurt. I hope not. You've all signed the waivers, right? You did sign the waiver when you came in. Okay, good. You saw them out there on the table. That's good. Okay. So first of all, the code here. We're using this API that we actually wrote a layer on top of this Paratier API, in which we use the metaphor of a brain, the drone brain. And so we have this command that we can give it, this takeoff method, and then we can tell it how long to hold, how many milliseconds to hold. And then we go right, the 20%, or the 20 is the percent of power. So go right for 20% of power, and do that for 1 second. And then hover for 4 seconds, go backwards, and so that would be a box pattern. Now here, we don't have much room for the box pattern, so I modified it a bit, and I'll show you the way I modified it here. If you look at in NetBeans, which is the way where I coded it from, let's see, where's the box? Yeah, demo flight box. What it's going to do, it's going to take off and hold for 3 seconds. Go over there at 20% power for 4 seconds, hover for 3 seconds, and then come back over here, not as far because I don't want it to come all the way over to here, for about 2.2 seconds, hold for 3 seconds, and land, right? So that's what it's supposed to do. We'll see what it really does. Okay. So, all right. And if it does happen to run into you, just bat it like this. You know what I mean? Don't try to grab the blades or anything like that. Yeah. Okay. All right. So now the drone itself has as I mentioned, has a wireless access point, and so right now we're hooked up. We're actually talking to the drone, and so here we go. Did I actually hit the run button? Oh, no. Hitting the wrong program. Okay, there we go. All right. Oh, wait a second. Uh-oh, something could go really badly wrong here. Okay. Okay, there we go. Okay. All right. Okay. Yeah, so we're gonna do that one more time a little bit later. And so you'll have a photo op. And if you want a photo op with yourself, just run up here, have somebody take your picture. You can run up here and do a photo op with it. So yeah, so it didn't connect. There was a connection error. And the reason why is there's something I would be showing you here with, it's an IoT concept and tool called MQTT. And I hadn't started that up yet. And so that's what it was actually connecting to. OK, so getting back to the presentation. If we wanted to, for example, have it fly around and do some autonomous kinds of functions, maybe go home, then we have this go home method. Now the go home, our level of autonomy is pretty crude. So the way that we're calculating go home is we're calculating what the commands were to make it go somewhere, right, left, holding, things like that. And then go home, we're just calculating what it would take to make it go home. So that's not going to compensate for wind currents or anything else. So but we'll talk about how we would deal with that later. But this go home, all it's doing is this would take off, hold for 6 seconds, go forward and hover, right and hover, things like that. And then we just say go home and land. Right? So this is a recording of going home or of doing that and then going home. Yeah, so that's that. And then it got kind of close. And then there's the LEDs. It can control the LEDs, the onboard LEDs. And so here are those LEDs. There are 4 of them, and they are red, yellow. Each of them can turn red and yellow and green. And so this is the code for doing that. So here we can play LED animation, maybe blink green, things like that, and while it's hovering. And so here's a video of it doing that. So if you look real close, you'll see the LEDs blink while it's hovering. Okay. So we wanted to leverage some Internet of Things concepts. So some of the things that we used, we used, for example, the Raspberry Pi. It's as I've mentioned, it's a $35 board that's great for being able to do projects, hook peripherals up to it, including the drone. There's also something called Mosquito, which it's an open source MQTT broker. MQTT is a protocol that's used for a lot of things, messaging, but it's really good for being able to use in Internet of Things, because you can publish and then subscribe to messages, and that's exactly what we're going to do. As a matter of fact, we're going to, if we were running the Raspberry Pi strapped to this thing, it would be running on that Pi, collecting information from the drone about speed and yaw, pitch, roll, things like that, and then communicating it over MQTT. And then we've got, this is MQTT here, FX. It's a client written by a colleague in Germany that is subscribing to a particular connection, and it will then display the different messages that were sent over. And so I'm going to go ahead and fly the drone again, starting up Mosquito, which is here. So that is what would be running on the Pi. It's running on my local machine here. And then I'm going to open MQTT, and we'll connect to local Mosquito here. And then we're going to subscribe to the A4J nav data messages. So any A4J nav data message that comes from the Pi that gets published and then read, we'll go ahead and show here. So I'm going to go ahead and start the application. And so, did I say subscribe yet? Yeah, there we go. Okay, so then, whoa, hey, get over there. No, get over there. So anyway, so there's the messages that that are coming over here. So there's some altitude from the ultrasonic transducer, the pitch, yaw pitch, roll, things like that that are coming from the IMU, again being published to the MQTT stream. By the way, if you have any questions while we're... Hey, you have a question.
Did it just record on the order of about 600 messages for each of those types?
Did it just record about...
I'm wondering about the number on the right. That's hypothetical.
Yes, the number on the right. Let's see. Let's see if... I was testing a little earlier, so let's look at the time date stamps here. We started at 1 o'clock, right?
So that's a sequence number. It's not the number.
That's a sequence number, but we started about 1 o'clock, right? So, yeah, actually it did. About 600 and some messages, right? Yeah. Other questions while we're... Okay. Good. I better pick this up so I don't step on it. Okay. So I kind of went through this with you, but the mosquito's running on the Raspberry Pi, you know, if the Raspberry Pi were strapped to it. And then we subscribed to the flight data. That was the kind of the model of that. And then we just demoed that. So now the 3D thing, the 3D simulation. I'll let Sean talk about that, but what that was for was so that this 3D simulator was so that we didn't have to continually fly the drone, wear out the batteries, you know, keep the batteries charged, things like that. And so I'll let him tell you about
Hi,
this.
everyone. My name is Sean Phillips.
He's a little bit of a
and
smart
I work
aleck,
for a
by the
company
way.
named AI Solutions. We provide access to space for both NASA, the U.S. Air Force, and other space agencies around the world. We're located just outside Washington, D.C. I was invited by Mark Heckler and Jim Weaver to help them with their Java 1 session this year titled Welcoming Our Robotic Overlords. Their bright idea was to take a bunch of 4 quadcopter drones and attach Raspberry Pis to them and then give them all the smarts that they need to go flying around the audiences without chopping people's heads off. And so far, nothing bad has happened. So in the meantime, they said, well, we're having a lot of trouble. It's a lot of work to try to test the code and try to get these drones to move around. It'd be really nice if we had a 3D simulation that could help us test some of this stuff. So instead of Mark Heckler flying his drone around in his living room in his house and breaking his lamps, he could instead fly it around on the screen and just break pixels. So they asked me for some help. So I decided to use JavaFX 3D. So I used a few libraries to do that, and Jim Weaver is going to demonstrate some of the software I made live and show you some slides to go with it. I won't steal his thunder, but I would like to mention a few technical items. First, I use a great model loading library called from Interactive Mesh. It loads 3DS, Collada, OBJ, etc. For this project, I have several OBJ assets in with the source project, a TIE fighter and an X-Wing fighter. You'll see that in a moment. For the 3D cube world that you see, I had that from FXYZ, which is a third-party, open-source JavaFX 3D component library, providing anything from 3D scatter plots to skyboxes to all kinds of shapes and billboards. And finally, it should be noted that the method for navigation I used is a simple form of dead reckoning. dead reckoning is essentially taking the taking the commands and the data that you receive from your real life system, i.e. the drone, and performing estimations and tracking those estimations. Now there's a problem with that, of course, and that is that if the estimations, in this case in the 3D world, don't match the actual world movements of the drone, there gets to be a cumulative error. That is an error that's adding up over time that you, as a dead reckoning system, can't determine. So that's one of the weaknesses of this current code, is it's dead reckoning around in the 3D world. So if you look to extend this example that we're providing with this presentation, please keep that in mind. The other thing to keep in mind is that we designed this code to be very flexible. The code was written in such a way that new commands could be built, defined, parsed with whatever rules that you would like to have. And so you'll see that it's very easy. I used NetBeans 8 to do that. Yeah, there it is. And you'll see that there are 3 really major classes you need to address. The autonomous 4J3D sets up the 3D scene, adds some mouse and keyboard handlers here, and accepts commands via drag and drop, as Jim is going to show, and then recognizes those commands and then issues commands to the drone. That's handled in the Overlord class. The Overlord defines your drone, and this is where you tell it to say, okay, if you receive this command, this is what you need to do on the screen. And you'll see that I've relied very heavily on transitions and translations, as you would expect in a 3D scene, but I also rely heavily on timelines and properties. And the reason for this is I couldn't use standard paths because the standard path in JavaFX is only 2D. It does not support 3D translations. So we kind of had to hand tool it a little bit. Finally, if you want to change how your drone moves, or if you have a different type of drone, you're going to need to play around with the formulas that perform the dead reckoning itself. And that is here, the sensitivity variable, and also the power, and to a certain extent, your duration calculations. All right, well, thank you for your time. I hope you enjoyed the demonstration, and back to you, Jim.
Okay. Again, I'll carry back any thanks that you have to Sean. Okay, thanks. All right. So he went through a lot of this about the Overlord class and some other things. I'm just going to go ahead and show you the software here. Go ahead and run it. But did I already start it? Yeah, I did. Okay, so what I went ahead and took a file. It's a flight recording file that was created during a box flight earlier, and I'm going to drag it into this 3D application, as Sean said here. Here we go. And then we'll see a simulation then of what that box flight was using a TIE fighter. So yeah, this saved us a lot of time, because then as we flew, we could, as we were doing simulations, we could just use this 3D simulator rather than having to fly the drone all the time. Okay? So the next step then would be more levels of autonomy. So as you've seen here, the autonomy that we went for was simply being able to have it be self-contained, take the Raspberry Pi, strap it on the drone, have it fly that way, and be able to give it commands like go forward, go backwards, hover for a certain number of seconds, go home, things like that. But if there were gusts of wind or other kinds of things that would take it off course, it would not know about that. So to get any higher levels of autonomy, we have to create something called a control loop. And so that'll be some of our next steps. So with the drone, it comes with an oriented roundel. And that's just a symbol here. It's on a piece of paper. You can put it on the floor. And using its downward facing camera, it can tell where it is in relationship to the oriented roundel. And when I say that, I mean it can report to you when you ask. It can report to you where it saw that, the fact that it saw it, what pixels in the camera in which it saw it, and then from that you can tell your angle from it using some linear algebra. You can tell your angle from it, you can tell your height, and you can corroborate that with the ultrasonic transducer, the ultrasound thing that measures your height. And then you can do like matrix multiplication and some other operations to be able to then tell in 3D space where you are in relationship to that. So your classical control loop is comprised of state estimation, so you're estimating where you are in space in this case, and then control. So I always like to think of it as like in the shower in the morning. You turn the water on and then you test it, and it's too cold, right? So you do some control to it, maybe turn it a little hotter, and test it again. Maybe it's still a little bit too cold, and then you do it again. Okay, it's fine, right? And then, but as you're taking the shower, it may get too hot, too cold, whatever, and so you're making these changes to the knob. So that's the same thing with this. The drone is somewhere in space, and maybe you want it to go to a pose of 3.5 meters in the x-axis, 4.8 meters on the right axis, and maybe 0.3 meters high in some position in XYZ space. You want it to go over there, and you want its yaw, you want it to be pointing at a 45-degree angle. So that's where you want it to go. And based upon, and it knows where it is because it can measure its error based upon what I just said about being able to find itself in space with the oriented roundel. And then you run it through a controller. And if anybody familiar with like PID controllers, anybody heard that? Okay, PID controllers where the P is proportional. So with the shower example, maybe you sense that there's a 20-degree difference. That'd be a lot, but 20-degree difference, I guess, from where you want it to be and where it is. And so you would do a gain on that proportionally to that difference. And so then the I and the D are integral and derivative, and there's some calculus kind of things that have to be applied to in that formula. But you're going to then figure out the change, the amount of control, so in terms of acceleration of X, Y, and Z axes to get from where you are to over there. And so then you apply that control to the drone. And that would be in terms of rotor speeds, because we just have 4 rotors to play with. And then we sense, while that's happening, we're using some odometry, like visual odometry because of the downward facing cameras, as well as odometry from the IMUs because of like accelerometers and the gyroscopes. And also for the yaw, we could use the magnetometer to know whether our yaw was correct. And so then we measure the pose again, where are we now? And we compare it to the desired pose, and we go through that control loop. And we do that until we arrive at where we want to be. Yes?
Can you parameterize your gain on your feedback loop to update or to based on your next measured values? Can you use those values to gauge whether you should increase your gain or decrease it?
Yes, part of the okay. So the question is, can you, like if you apply a gain and then you do another measurement, can you use those measurements to then decide what gain to use again, and kind of and yes, it's a constant feedback loop to where you're constantly changing your gain based upon your algorithm, your PID algorithms, and there are a lot of them, and you can change your gain and do that as you're, in flight, so to speak. Yeah.
Learn if you change the payload.
Yes.
And the characteristics change.
Yeah, so you could learn if you, for example, if you change the payload and the flight characteristics and things like that. Yes, that is feasible. You know more about PID control than I do, so you're going to ask me a question, and I'm going to say, give me your best guess on what the answer is. So what's your question?
So mention the controller. The controller code is writing inside the chip or is inside the pipe. That's
Right. So the question was, where is the controller code? So we haven't written that yet. This is something for the next step, and when we do that, it will be for the Pi, right? So it'll be on the onboard brains rather than inside of the drone itself. Because so this controller code. That's a very good question. Okay, so if you think about this control loop, there's actually two control loops. There's one that's happening right now, and there's one that I want to add later that it's going to be able to do this kind of thing, right? So this doesn't exist yet. I haven't created that yet to where I can say, go to XYZ of 153, But what is on board the drone right now is a control loop that tries to stabilize its flight. So as you saw, it was trying to stabilize its flight. It was trying to stay pointed in the same direction. And so in the motor controllers and in the control itself, it has that kind of, I don't know whether they're implementing PID control, but there is some kind of controller that tries to maintain level flight and things like that. So that does exist. But this other thing that I'm talking about, where we make it autonomous and go fly over there and tell where you are, I haven't implemented that yet. Yes, good. Yes, question.
And I'm speculating, and hopefully.
Okay, then I'll speculate with an answer.
Is the ideal case for a really good implementation of a PID control to basically propose a flight plan, and then over time, as it repeats that flight plan, it adjusts it to actually go where you told it to go? So
Yeah, so like
earlier example, you basically go to this altitude, adjust power 20% this way to go that way. Over time, I would imagine it would get smarter and know that 20% power is too far to go that distance, 15% is all I need, etc.
Here's what I know about PID control, and then my colleague here will have to tell you more. Is that you have this algorithm in which you configure different things like gain and other things, and then it tries to do what you're doing. It measures and then applies control based upon the parameters you've given it, and then as far as self-learning and adaptive and things like that, I don't know enough about the domain to tell you, but my colleague here does. So, or this colleague, somebody would probably, or maybe you, would probably know about that. So please enlighten me and help this gentleman with his question. Yes?
Is the Phantom, is it using like a KK controller where I believe they have like an artificial horizon that they do a feedback loop against. Like here's the ideal. That's at the low level. The reflex.
The Parrot just uses gyroscopes and things like that for that. Yeah. Yes.
Where is code for image recognition?
Where is the one?
Yeah, who does image recognition? Raspberry Pi or internal controller of the culture?
Okay, where's the code for the what position?
Face that is reference.
Yes.
Copter sees it.
Yes.
And it does image recognition.
Yes.
Know its position.
Oh, image recognition. Yeah, okay. Right. So so the question is, where is the code for the image recognition? So the Parrot drone has actually actually 3 different tags that it's able to recognize. There's this one, actually 4. There's this one, and then there are 3 tags that you put on the sides of other drones so they can recognize each other as they're flying, and you can do some augmented reality games and things like that. But the image recognition code is actually on board. So when you're talking to the drone, it is reporting, hey, I found a oriented roundel, and here's where it was. Here are the pixels that I found it. The 4 pixels that define where I saw it in my downward-facing camera. And based upon how high I was and things like that, then I can tell where I am in space. I have not tried to hack it, no. We're doing just fine to make it do what it just did. Yes?
When you're going like brain go right, I'm assuming that's the API that you decided to use for that.
This brain, this A for brain, autonomous 4J brain, that's the one that we wrote, and it's a kind of a layer on top of then the Paratier API.
So that Paratier API is, do you like provide it like the speeds that you want each one of the blades to rotate at, or like, can you control that? Like, I'm thinking if you can control those blades, like in theory, I guess you could flip it upside down and maintain stable inverted planes. If you're controlling that, or is that the drone itself that's taking like these move for this amount of distance?
Right. So the question is, in what levels of the software are the ability to change the rotor speeds? So at the brain class level that we wrote, we defined that to have percent of rotor speed, or percent of speed, right? And so then underneath, then the Paratier does the same thing. We just actually give it the same. We say, go a certain direction at a certain percent. And then the Paratier API talks directly to the, using a protocol over TCP/IP, a message-based protocol, to the drone itself that then gives it commands that are at a lower level. And I can't recall, all the commands there. As far as flipping the thing over, there is a safety thing in the drone itself. If it gets over a certain angle, it'll shut down. Okay. One more question. Okay, so your question, the gentleman in the second row, I'm going to have to take that offline. Maybe actually asking the colleague in front of you. Very good. So, hey, I guess that's it. So thank you for attending.